Video is going to talk about vectors and what is a vector, how to find its component form, and also talking about its magnitude. Now, a vector is a directed line segment made up of magnitude and direction. Okay? And to help us with vectors, I'm going to do a little bit of scratch work ahead of time here, just reminding us of a simple formula that we already know, and it's called the distance formula. If you remember, the distance formula is d equals the square root of x2 minus x1, so basically subtracting our two x coordinates, squared, plus y2 minus y1, also squared. It's very similar to a Pythagorean theorem, right? If this was a squared and b squared, and if we were equal to c squared, only we took the square root, turned that into d up here, and again, by taking the square root on the other side, we get this long formula going on. All right, we get that big formula on the other side there. Well, very simply, if we plug our points in, d equals the square root of, I'm going to take the x coordinates, so 4 minus negative 1, so it becomes plus 1, squared, plus, again, y is negative 7 minus 5 squared. Doing a little bit of calculating. Again, 4 plus 1 is 5, so squared would be 25. Plus negative 7 minus 5 is negative 12. Squared is 144. And that's the square root of 169. That'd be 13. Very simply. Now, the reason I did all of that work is essentially to find the component form of a vector, such as down here at the bottom, and the magnitude of a vector, okay, such as the formula here. We're essentially using that distance formula idea. Because if you want to draw a vector, and again, I'm just going to give myself an axis here. So I'm going to draw out a coordinate plane. All I would have to do is plot my points. So P is negative 1, 5. That'll be our point right here in the upper corner. And Q is 4, negative 7. Now that's going to be a little bit off my graph, but there would be point Q. And the vector is the magnitude and direction. It's the line directly from P to Q. And again, I'm going to attach an arrow on this end. Now it's not longer than that. That's not why I'm drawing the arrow. The arrow is representing the direction. Sometimes you'll even see people draw the arrow in the middle of the line. Just to remind us, we went from P to Q. We traveled in that direction. A vector, again, has magnitude, which is essentially the length. Well, it makes sense. That would be the distance formula, right? That distance, that length between P and Q. It also has direction. Now, we'll talk more about direction in a future video, but just realize for now, we've traveled from P to Q. We're traveling in that direction, right? The vector doesn't just sort of willy-nilly travel wherever, and it doesn't go backwards. A vector has direction from one place to another. Now, the component form of a vector is a way to represent the vector, and notice we kind of have that part of our formula. Q minus P and Q minus P is kind of like saying x2 minus x1 and y2 minus y1. We're just subtracting, right, sort of the x coordinates. Now, the couple of things I want you to notice, when we're representing a vector P to Q, we say P, Q, and then we sort of put this half arrow above it. That's a vector symbol, okay, that little half arrow. So notice down here we've got that P to Q, little half arrow. And we're also saying Q minus P. Well, Q1 minus P1 would be sort of like the horizontal, right, the x coordinate. So 4 minus the negative 1, comma, and negative 7 minus 5. And we put that sort of angled bracket. It's not a parenthesis. These aren't coordinate points. It's a bracket, sort of this pointed bracket to say, well, 4 plus 1 is 5, and negative 7 minus 5 is negative 12. In order to get from P to Q, we traveled 5 units to the right, and we traveled down 12 units, right? So again, that's that horizontal component, 5 units, and vertical component, negative 12 units. So the component form of a vector is just separating it into sort of horizontal and vertical. The magnitude of a vector, on the other hand, is to take those coordinates, take those horizontals and verticals. Notice we called them here A and B. And we would take the square root of, right, A squared plus B squared, negative 12 squared here, which is 25 plus 144, the square root of 169, and essentially we get 13, right? That's that length of the vector. So finding the component form and then finding the length or the magnitude of the vector, right, is kind of like just doing that distance formula, but with a different purpose here. Now you'll also notice over here I called this V, so it'd be kind of like saying, well, vector P to Q, well, that's great to represent from point to point, but the actual vector, right, if we wanted to give it a name, we could call that vector V, right? We're just giving it a name, vector V there. And oftentimes in a book, you'll see that it's just a bolded, statement. When we're writing, we can't really write in bold most of the time, so we just give it that V with that half arrow above it, right? A vector V. Let's do that one more time. And then in a future video, we can talk a little bit more about drawing vectors and kind of the importance of how to draw them, as well as what's called a unit vector. So make sure you watch the following videos as well. But let's practice this once. So we want to draw vector RS. Well, if they're going to give us exact points for R and S, we should probably graph that out. Negative 1, 2, 3, and up 1, 2, 3, 4. Now you might wonder why I made those so small when I got all this space. Well, notice that point S is 2 units to the right, but it's 8 units. 1, 2, 3, 4, 5, 6, 7, 8 units down. And I'm just trying to make sure we can fit that on the screen here. So again, this is to get from R to S. And notice it's traveling down to the right there. The component form, again, bracket there, is to take the S coordinate minus the R coordinate, which again, minus the negative 3 became positive. Again, negative 8 vertically minus 4 vertically. And our component form of our vector just happens to come out, same as the one did on the previous screen, to 5, negative 12. So actually, this vector is the exact same vector we just drew on the previous screen. We just had a different starting and ending point. But it's really the same vector. It's an equivalent vector. It would have the same magnitude. Again, the magnitude with these double bars for RS. Okay, almost looks like an absolute value, but it's sort of that double bar. It's a symbol for magnitude. You might have seen it on the previous screen. Is equal to the square root of, again, 5 squared plus negative 12 squared, or the square root of 169, basically comes out to 13. So the magnitude of the vector, again, that double bracket, double bar there, is equal to 13 units long. Now, because we can draw a vector really in any spot or any position, right, what we can actually do is draw them in what's called standard position. A standard position vector is one that has an initial point at the origin. So instead of being up where R is in this first top screen, we're going to start from the origin. But then what I really want, right, is this exact same vector that I've already drawn, right, only I want that down below here. So what I'm going to do is I'm actually going to draw it in blue. I'm just going to trace this again. If I follow that vector, let's see if I can grab hold of that blue vector and just draw it, again, from 0, 0. That would essentially be our vector in standard position. It's 5 units to the right and negative 12 units down, right? Down here. Now, I hope that helps you finding the component form of a vector and the magnitude of a vector. Again, make sure you watch the future videos. They're also going to talk about what's called a resultant and also what's called unit vectors, and they're also going to help you in your homework tonight. If you have any questions, talk to your teacher. Otherwise, watch those other videos and have a great day.